Across the dark edge of the Milky Way, one star is breaking free, moving so fast it's escaping our entire galaxy. This is US 708, the hypervelocity star racing through space at deadly speed. How did it reach such impossible velocity? If you enjoy mysteries like this, please like, subscribe and share, and tell us in the comments, what would you name a star that defies the galaxy itself? Thank you for watching. Now, let's begin. The Milky Way appears as a broad pale band in the night sky, yet as a galaxy, it holds a layered structure that extends far beyond the bright disk that most eyes imagine. A thin, star-filled disk rotates like a slow wheel. A central bulge swells around the heart of the system. Outside both lies the stellar halo, a vast faint spheroid of old star clusters and long tidal streams that wrap the galaxy like gauze. The halo reaches to distances measured in many tens of thousands of light years, and it contains only a trace of the total starlight. Its stars are sparse metal poor in the language of stellar chemistry, and arranged not in a plane but in a diffuse cloud that barely glows. In this region, the gravity of the Milky Way is still present and strong, yet its pull is spread over great scale, and the motions of halo stars record that pull in slow arcs that cross above and below the disk. To understand any star that moves through this realm, the first idea to set is escape speed. Escape speed is the smallest speed an object must have at a given place to break free from the gravity of a larger body and never fall back. On Earth, a stone thrown fast enough rises without returning. Inside the galaxy, the same principle holds, but the landscape of gravity is not shaped by a single sphere. The Milky Way's gravity comes from the mass in the luminous disk and bulge, and from a much larger unseen component that astronomers call dark matter. The combined mass makes a gravitational field whose strength changes with position. Near the center, where mass is concentrated, the escape speed is higher. Far out in the halo, where the pull is weaker, the escape speed is lower. This changing threshold creates an invisible boundary in speed rather than in space. Whether a star is bound or unbound depends on how fast it moves compared with the local escape speed at its present location. A star that moves more slowly than this threshold may travel on a wide, long orbit that keeps it within the galaxy. A star that exceeds the threshold is not held. Its path bends under gravity but never closes, and over long time it departs into intergalactic space. Because the threshold varies, a single number cannot describe it for the whole galaxy. Close to the central bulge, the required speed is large. In the outer halo, the required speed is smaller. For a given star, what matters is the escape speed where it is now, and the speed the star has when measured in the correct frame for the galaxy. The halo is a natural stage to study these ideas because its low density gives stars long clear paths. Streams from past mergers thread through it like faint rivers. Globular clusters drift along old orbits. Individual stars pass in quiet, watched by surveys that map their positions and motions. The absence of thick dust and gas that crowd the inner disk means that measurements are less hindered by obscuring material. In the halo, speed is not masked by swirl and crowd. When astronomers speak of hypervelocity stars, they mean objects whose speeds are high enough to exceed the local escape threshold of the Milky Way. The term is not a flourish, it marks a physical status. A hypervelocity star is not just fast, it is unbound. This is a definition rooted in the gravitational field of the galaxy and in the measured motion of the star. Calling a star hypervelocity then is equivalent to saying that its present speed relative to the galaxy is above the boundary needed to leave and not return. The concept rests on two pillars that observation can supply. The first pillar is the structure and mass distribution of the Milky Way, which set the escape speed at each location. This distribution is inferred from many lines of evidence, including stellar motions, the rotation of the disk, the orbits of satellite galaxies, and the shapes of tidal streams in the halo. The second pillar is the motion of the star itself, which must be measured along the line of sight and across the sky to build a full three-dimensional velocity. With these two in hand, the comparison becomes possible. The choice to begin with the halo is practical as well as conceptual. The halo defines the quiet boundary conditions of the Milky Way. It frames what it means to be bound. It is where gravity still rules, but other effects become small. In the disk, gas clouds and spiral patterns can pull and scatter stars. Near the centre, the crowding of stars and the deep potential well complicate every measurement. In the halo, the main influence is the large-scale mass of the galaxy as a whole. A star that crosses this region at extreme speed traces a clean test of binding. Its path is not diverted by dense gas. Its light is not heavily reddened by dust. Its motion can be measured over years by watching its position shift on the sky, while spectra taken with large telescopes reveal how quickly it approaches or recedes. These measurements are made in careful steps. Positions are mapped at different times to detect tiny changes that add up. The halo's emptiness, far from being a lack, is the condition that allows these changes to be seen. The halo also carries memory. Many of its stars were formed in small galaxies that later were drawn in by gravity and torn apart. Their debris stretches into streams, and those streams act like trails of sparks that sketch the pull of the Milky Way over vast times. By fitting the shapes of these streams, astronomers infer how mass is spread through the halo and beyond. That knowledge feeds directly into estimates of escape speed at various radii. In this way, the halo provides both the canvas and the scale for the problem of unbound motion. To picture the boundary in simple terms, imagine a nested set of shells around the Milky Way. At each shell, the escape speed takes a different value that reflects the mass interior to that shell. A star starting from that shell, with a speed below the local value, arcs around, and remains within some inner shell. A star with a speed above the local value arcs outward and does not close its path. Observers do not draw these shells in space, but the idea helps fix the meaning of hypervelocity as a local comparison rather than a single universal mark. The halo's vast extent also means that an unbound star can spend long time under the galaxy's influence, while still on a one-way path. Gravity slows it, but cannot reverse it once the threshold has been surpassed. Farther out, the pull weakens, and the star continues into the space between galaxies. The timescales are long when measured in years, yet the conditions remain simple: low density, smooth potential, sparse encounters. From this vantage, the first task is to define with care the terms of the boundary. The Milky Way is the mass that sets the field. The halo is the region where that field can be read cleanly. Escape speed is the threshold that divides bound from unbound motion. A hypervelocity star is one that crosses that threshold at its current place when its motion is measured against the galaxy, rather than against the Sun or Earth. With these pieces set, the stage is prepared to consider any particular track across the halo, to follow how positions and speeds come together to indicate whether a star is held or free, and to do so without appeal to drama, only to the quiet arithmetic of motion in a known field. Bound and unbound describe two simple outcomes under gravity, and the deciding factor is speed compared with the local escape speed. Escape speed is the smallest speed an object needs at a given place to climb forever against the pull of a mass without turning back. In a galaxy, the mass is not concentrated in a neat sphere but spread through a rotating disk, a central bulge and an extended dark matter halo, so the escape speed changes from place to place. Near the center, where mass density is high, gravity is deeper and the required speed is large. Farther out in the faint halo, gravity is shallower and the required speed is smaller. This position dependence means that bound and unbound are not labels attached once for all places. They are assessed locally by comparing a star's present speed with the threshold set by the mass interior to its position. A star can carry great speed and still be bound if it travels where the threshold is higher. The same star could be unbound if it reached a region where the threshold is lower while keeping a speed above that boundary. The idea is a local test performed at each point along a path. In practice, the threshold is calculated from a model of the galaxy's mass distribution. The disk adds to the pull mainly within a few tens of thousands of light years. The bulge contributes in the inner region, and the dark matter halo extends far outward and dominates the pull across the halo. The gravitational potential, which is the stored pull per unit mass, combines these components, and escape speed at a position is related to how deep that potential well is there. Deeper well, higher escape speed. Shallower well, lower escape speed. Astronomers infer the shape of this well by tracing how stars and gas move, and by following the paths of satellite galaxies and long tidal streams that wind through the halo. Those motions act as test particles. When a mass model reproduces many independent tracers, confidence grows that its predicted escape speeds are close to reality across the regions constrained by the data. With a threshold in hand, the classification of a star as bound or unbound is the second step. The velocity used in the comparison must be the star's velocity with respect to the galaxy, rather than with respect to the Sun, and it must be the full, three-dimensional speed, not only the component along the line of sight. Once that speed is known, the question reduces to a clean inequality. If the speed is below the local escape speed, the orbit is bound. If the speed is equal to or above it, the orbit is unbound. Bound orbits come in many shapes, from near circles to long thin ellipses, but all close on themselves under gravity and remain within the potential well. Unbound paths are open. The star may slow as it climbs the well, but if its speed exceeds the threshold at each point along the way, the path does not close and the star departs. Because the galaxy's pull weakens with distance, a star that is unbound at one point remains unbound as it moves outward. The threshold continues to drop while the star retains at least part of its speed. The region where escape speed is evaluated matters for any comparison. In the inner disk, spiral structure, gas clouds, and stellar crowding can add small extra tugs that complicate motion on short scales, though they do not overturn the large-scale threshold set by mass. In the halo, where density is low and encounters are rare, those extra effects become negligible, and the smooth gravitational field dominates. There the local test becomes especially clear because there is little else to push or slow a star besides the galaxy itself. For this reason, the halo is a natural laboratory to separate bound from unbound motion, using the escape speed concept alone. The distinction between fast-bound stars and hypervelocity stars follows directly. Many halo stars move at high speed relative to the Sun because the Sun orbits in the disk, and the halo population has different typical motions. A high speed measured this way does not by itself tell whether a star is bound. The relevant speed is the speed with respect to the galaxy, and the relevant threshold is the escape speed at the star's position. A halo star can move at several hundred kilometers per second, and still be deeply bound if the local threshold is higher. A hypervelocity star is one whose speed with respect to the galaxy exceeds the local threshold for escape. The term hypervelocity is not based on a fixed number shared by all radii. It is tied to the local value which declines outward. This clarifies why some objects with similar measured speeds can fall into different categories depending on where they are and in which frame their speeds are considered. The threshold itself is not known with absolute precision because the mass distribution of the galaxy is measured with uncertainties. Models differ in how concentrated they make the dark matter halo in the thickness and mass of the disk, and in the exact profile of the bulge, and these choices shift the predicted escape speed by modest amounts at a given radius. Observers account for this by carrying a range of plausible thresholds through their analyses, and by quoting whether an object is unbound within a given model family. Even with this caution, the separation of bound from unbound remains robust when speeds stand far from the threshold. The grey zone near the boundary is where classification can depend on the chosen mass model and on the precision of the measured star speed. In that zone, improved measurements and better constraints on the mass distribution move the answer from tentative to firm. Energy language gives the same picture in another form. The sum of a star's kinetic energy and gravitational potential energy sets whether the orbit is closed or open. An orbit is bound if the total is negative, which means not enough kinetic energy to climb out of the well. An orbit is unbound if the total is zero or positive, which means just enough or more than enough energy to depart. Escape speed is simply the speed that sets the boundary between these cases at the current position, translated into plain words as the least speed needed not to return. This energy view and the local speed comparison are equivalent ways to state the same physical test. A practical case helps fix the logic. Consider a star in the halo with a speed of roughly 1,000 kilometers per second, with respect to the galaxy moving at a distance where a common mass model gives an escape speed of around 600 to 700 kilometers per second. The inequality is clear in this neighborhood of values written in words. The star's speed is above the threshold and the path is unbound in that model family. The same star placed much deeper in the potential well without changing its speed could be bound if the threshold there rose above that speed. The classification depends on the local comparison, not on a universal mark. This thought exercise underlines why the exact location and the underlying mass model matter for any firm statement about bound or unbound status. Across the halo, the threshold declines gradually with radius, while the possible star speeds span a wide range. So the border between fast-bound and unbound objects is not a single line, but a surface in position and speed space. In quiet conditions, the comparison is straightforward. The halo contains little gas, so drag forces do not play a role in changing the outcome. Encounters with other stars are exceedingly rare and weak at these densities, so gravitational nudges do not usually shift a star from bound to unbound or the reverse. A star crossing the halo traces a slow drift on the sky that can be followed without knowing how fast it moves along the line of sight. The drift is called proper motion, a small change in apparent position against the fixed pattern of distant galaxies. It is measured by comparing precise coordinates recorded at different times and by fitting a straight trend to those changes. For a target in the sparse halo, crowding is low, so the point spread of the star is clean and the background is stable. Over years, the small shifts accumulate into a measurable displacement, and that displacement per unit time marks a direction and an angular rate across the celestial sphere. With only this information, a wide-angle track can be drawn. The direction of the motion defines a great circle on the sky, which is the largest possible circle on a sphere, and the path followed by a point moving at constant direction in 3 dimensions when projected outward. The current position of the star sits on that great circle. The proper motion vector sets its tangent at the current location. Extending the tangent both forward and backward draws a full arc that is independent of any radial component that is not yet considered. This construction is purely geometric. It relies on angles and directions. It does not require distances or speeds in kilometers per second. It is the first map of the path as seen from outside. To place this arc in a galactic setting, the coordinates of the star can be converted from equatorial to galactic longitude and latitude, which align with the plane and poles of the Milky Way. In that frame, the Great Circle can be described by its pole, a point on the sphere 90 degrees from every point on the circle. The pole is set by the cross product of the unit vectors for position and proper motion direction, expressed in plain words as the unique point that is perpendicular to the plane of motion. Once the pole is known, the Great Circle is fixed, and the star's sky path relative to the Milky Way plane can be drawn without reference to speed along the line of sight. Where the Great Circle intersects the galactic plane marks two nodes. Projected backward in time, the star's sky path approaches one node. Projected forward, it approaches the other. These nodes do not by themselves provide a physical crossing in space, because distance is not yet included, but they provide a clean geometric reference that anchors the arc within the galaxy's face-on view. The proper motion gives not only direction, but also an angular rate in units of angle per year written in words. Combined with an estimate of distance, that rate would become a transverse speed, but here the distance is held back and only the angular trace is used. Over a span of years, the cumulative angular shift can reach many times the measurement precision, strengthening the reliability of the fitted direction. Because the halo has little dust and few bright neighbours at high galactic latitudes, the measurements are less affected by variable extinction and blending. The star's point-like image moves steadily, and the background pattern of galaxies provides a stable grid against which to measure the drift. This setting allows a clean determination of the arc without resorting to complex modelling. Wide surveys that repeat measurements over time produce catalogues of positions at multiple epochs. By aligning the images with a reference frame that is tied to distant galaxies, residual systematic shifts are reduced. The star's positions at these epochs plot a near straight line on small scales. The slope of that line corresponds to the proper motion vector. Its uncertainty reflects the scatter of the points and the known measurement errors in each epoch. Even before any line of sight speed is added, the arc defined by this vector carries information about the likely large-scale path through the halo when projected on the celestial sphere. The arc can be extrapolated backward in angle to see which broad region of the sky it came from, and forward to see where it heads. When the arc is overlaid on a map of the Milky Way in galactic coordinates, it often cuts across the plane at a noticeable tilt, which is common for halo trajectories. The angle between the arc and the plane at the node encodes the inclination of the projected path. A steep angle means the path is strongly inclined relative to the disk. A shallow angle means it runs nearly along the plane in projection. Neither case fixes the true three-dimensional inclination, but the projected tilt is a useful descriptor of the apparent geometry. The Great Circle approach assumes that the direction of motion on the sky is approximately constant over the time span of measurement. In the smooth gravitational field of the halo, this is a good approximation because the path curves only on scales much larger than a few years of observation. Over such a short arc, the change in direction is slight, and the straight-line fit captures the local tangent. Over longer spans, small curvature from the galaxy's pull could be detected, but that refinement is not needed to set the wide-angle track that guides the analysis at this stage. The arc also has a natural uncertainty band set by the uncertainty in the proper motion direction. When that uncertainty is small, the band is narrow and the arc is well defined. When the uncertainty is larger, the band widens and the backward and forward projections sweep broader regions on the sky. This banded arc is an honest picture of what the measurements support. It shows where the star's projected path most likely lies, and how that likelihood spreads with distance from the current position. By comparing the arc with known structures in the halo such as tidal streams and the outlines of satellite systems, one can describe whether the projected track crosses or avoids these features in angle. Such comparisons remain purely geometric here. They note overlaps on the sphere without drawing physical links. The sparse field helps once more because few structures crowd the line of sight at high latitude, and the arc can be traced across large swaths of the sky without confusion. The star's current latitude and longitude in the galactic frame sit as a single point on this arc. The proper motion direction at that point points along the arc toward increasing or decreasing longitude depending on the orientation. The two nodes where the arc meets the plane can be labelled by their longitudes, and the latitudes there are by definition 0 in this frame. The arc's pole, located at high latitude on the opposite side of the sky from the direction of motion, serves as a compact way to encode the plane of the projected path. All of these elements are set entirely by position and proper motion, which are the only ingredients permitted at this stage. Distance and radial motion remain off the page until later. Without distance, the angular trace does not yield a travel time or a transverse physical speed. It does, however, yield a consistent map for the direction of motion that any later additions must respect. Any future inclusion of distance or line of sight speed must project back onto this same great circle when seen on the sky. In this way, the proper motion arc acts as a scaffold. It fixes the orientation of the path, locates the nodes where the projection meets the plane, and marks the broad angular corridor followed by the star across the face of the Milky Way when viewed from Earth. The curve is defined by the measured drift and by the geometry of the celestial sphere, and it stands without appeal to assumptions about internal properties or detailed origin. Motion along the line of sight completes what motion across the sky begins, and the quantity that records it is radial velocity. Radial velocity is the rate at which a star approaches or recedes from the observer along the direct line connecting them. It is inferred from the shift of absorption or emission features in the star's light, which slides slightly toward longer or shorter wavelengths when the star recedes or approaches. The sign of the shift tells the direction along the line of sight, and the amount of the shift compared with laboratory values measured on Earth tells the speed along that axis. With this single number and the proper motion already traced on the sky, the three-dimensional direction of travel can be set in geometric terms. The path on the celestial sphere provides the tangent direction across the sky. The radial velocity adds the component pointing inward or outward along the viewing axis. When both are present, the velocity vector points in a definite direction in space rather than only in angle. To translate the angular drift into a physical transverse speed distance is required. Proper motion gives an angular rate, which is an amount of angle per unit time written in words. If the star lies at a known distance, this rate corresponds to a sideways speed in kilometers per second that scales linearly with distance. A larger distance paired with the same angular drift means a larger sideways speed because a fixed angle covers more physical length farther away. A smaller distance with the same angular drift means a smaller sideways speed. In this way, distance acts as the lever that connects the sky trace to a physical speed on the plane of the sky. When distance is estimated, the transverse speed and the radial speed can be combined into a space speed through simple geometry. The transverse component lies on the plane of the sky in the direction of the measured proper motion. The radial component lies along the viewing line in the direction set by the sign of the shift. Together they form a right-angled pair whose squared magnitudes add to the squared magnitude of the total speed. Expressed in plain words, the total speed is the length of the diagonal of a box whose sides are the transverse speed and the radial speed. No special symbols are needed to hold the idea two perpendicular components build a single straight line in 3 dimensions. The direction associated with this line is also fixed once both components are known. It points where the star is actually moving in space rather than where it only appears to drift on the sphere. The geometry can be cast in the galactic coordinate frame, which places longitudes along the plane of the Milky Way and latitudes above and below it. In that frame, the proper motion splits into a part that changes longitude and a part that changes latitude. The radial velocity points along the line that reaches from the Sun to the star at its present position. The 3 together define the velocity components in the axes of longitude, latitude, and line of sight. Projected onto the face of the Milky Way, the transverse motion shows how quickly the star slides in angle, relative to the disk and toward or away from the galactic poles. Along the line of sight, the radial motion shows whether the star is coming closer to the observer or moving farther away right now. The combination is the minimal set needed to specify a full instantaneous motion in space. Distance estimates for halo stars can come from several routes that do not require any details that anticipate later regions. Photometric distances compare the observed brightness to an expected intrinsic brightness for a star of the same kind, then adjust for extinction by dust, which is small at high galactic latitude. Parallax distances measure the tiny yearly wobble of the star's apparent position as Earth moves around the Sun, turning that angular wobble into a direct distance. Either method, when available at useful precision, provides the lever for converting angles to kilometers per second. In the halo, where dust is thin and crowding is low, these distance methods are often cleaner than they would be in the inner disk. Once a distance is in hand, the arithmetic that leads from proper motion to transverse speed is straightforward. The star's angular drift per year times the physical scale per unit angle at the measured distance gives the sideways kilometers per second. The radial velocity from the wavelength shift provides the inward or outward kilometers per second. The quadrature of these 2 perpendicular speeds gives the total space speed measured in the observer's frame at this instant. This is a snapshot quantity. It states how fast and in what direction the star moves, now not a long-term average. It is enough to say whether the star is on a swift outward track on a fast pass by the Sun, or on a steep climb out of the galactic plane when read together with the position in the halo. The same construction also defines a spatial flight path that can be extrapolated linearly over short times if gravitational curvature is negligible on these scales. Over years, that is usually safe in the smooth halo field. Over tens of millions of years, curvature matters, but the present task stays at the scale where the instantaneous vector is the central object. The vector can be reported as a speed and 2 angles in the galactic frame, or as 3 component speeds along the axes of that frame. Either description is complete. The component form is often useful because it shows directly how much of the motion contributes to longitude change, to latitude change, and to radial approach or recession. The angle form is compact and intuitive, showing the direction as a point on the sphere and the speed as the length attached to it. Both follow directly from proper motion distance and radial velocity. Measurement practice assigns uncertainties to each ingredient. Proper motions carry small errors from position fits at multiple epochs. Distances carry errors set by parallax precision, or by the spread in intrinsic brightness for stars of a given kind used in photometric estimates. Radial velocities carry errors from the placement of spectral features. When propagated through the geometry, these errors widen the allowed range for the transverse speed, the total speed, and the direction angles. The result is not a single line in space, but a narrow cone or an elongated ellipsoid that contains the likely true velocity vector. The width of that region reflects the quality of the inputs. In the sparse halo field, repeated measurements over years can narrow the proper motion error. Longer parallax baselines can tighten distance. Sharper spectra can reduce radial velocity scatter. Each improvement contracts the uncertainty volume that surrounds the velocity vector. The presence of radial velocity changes the interpretation of a given proper motion dramatically. A star with modest angular drift but large outward radial speed can be moving much faster in space than the sky trace alone suggests. A star with large angular drift but small radial speed can have most of its motion in the plane of the sky, gliding sideways across the line of sight. The balance between the two shapes the actual path through the halo and determines whether the star is heading outward from the Milky Way or skimming past the Sun on a steeply inclined trajectory. Without the radial component, the wide-angle great circle of motion is known, but the sense along the line of sight remains unresolved. With the radial component, the sense is fixed, and the movement becomes three-dimensional in full. For a target that exhibits very large radial recession, the line of sight dominates the speed budget, and the star is climbing the galactic potential mainly along the observer's axis. For a target with very large transverse speed and modest radial motion, the climb is mostly sideways relative to the observer, and the path in space leans strongly across the sky. In either case, the construction remains the same. In the end, the completed kinematic picture at this stage is a velocity vector in space derived from proper motion distance and radial velocity, accompanied by a quantification of its uncertainty. It is a present-tense description that does not require knowledge of the star's internal properties. It draws only on position, changes a measured shift of spectral lines, and an estimate of distance. It stands in plane relation to the halo setting in which the star moves through a low-density environment under the smooth pull of the Milky Way, and it provides the immediate description of motion needed for any further analysis that depends on speed and direction in 3 dimensions. Light from a distant star reaches the telescope as a narrow beam spread by optics into an image, and when passed through a dispersing element into a spectrum. A spectrum is the star's light sorted by wavelength, recorded as intensity versus wavelength along a detector. Medium-resolution instruments separate nearby features with enough detail to measure line positions and general shapes. High-resolution instruments split lines, finally revealing their cores and wings and subtle asymmetries. The resolution is set by the instrument's design, and is given in words as the ability to distinguish close wavelengths. Higher resolution yields sharper line profiles and more precise velocities at the cost of fainter per-pixel signal. Observers balance these needs by choosing instruments and exposure times that match the target's brightness and the scientific goals. Before any measurement is taken, the instrument response must be calibrated. Calibration frames record the detector's dark current and pixel sensitivity pattern. Flat fields taken with uniform illumination map how the system transmits light across the detector. Arc lamps or laser combs provide reference lines at well-known wavelengths that anchor the mapping from pixel to wavelength. Observations of a spectrophotometric standard star set the scale for flux as a function of wavelength. Over the course of a night, the instrument may flex or drift by small amounts with temperature and gravity, so reference frames are repeated to track shifts. All of these steps turn the raw counts on each pixel into a spectrum that carries trustworthy wavelengths and intensities. The star's spectrum contains absorption lines where specific atoms and ions in its outer layers remove light at certain wavelengths. Hydrogen leaves a series of broad features in hot stars. Helium contributes lines in neutral and ionized states at characteristic places. Metals in stellar language, which means all elements heavier than helium add many narrower features, some strong, some weak, spread through the optical and ultraviolet ranges. The pattern of which lines appear, their depths, their widths, and their relative strengths provide the clues for both motion and composition. For motion along the line of sight, the spectrum is measured against laboratory wavelengths. A uniform shift toward longer wavelengths signals recession. A uniform shift toward shorter wavelengths signals approach. The amount of the shift averaged over many lines gives the radial velocity. Weighting the average by line strength and by the quality of the fit reduces random errors. High resolution improves this step by defining line cores cleanly, and by reducing blends where two features overlap. Corrections are applied for the motion of the Earth around the Sun and the rotation of the Earth during the exposure, so that the result refers to a standard frame tied to the solar system barycenter. This housekeeping ensures that the measured radial velocity reflects the star's own motion rather than the observer's vantage. The widths and shapes of lines carry additional information. Thermal motion in the gas broadens lines in a predictable way that depends on temperature and the mass of the absorbing species. Pressure broadening arises from interactions in dense layers and changes the wings of lines. Rotation spreads the light over a range of wavelengths because parts of the surface move toward and away at slightly different speeds. This effect gives a characteristic rounded profile with edges set by the projected rotational speed. Turbulent motions in the atmosphere of the star add a micro and macro component that broaden and sometimes skew profiles. The instrument itself adds a broadening kernel that must be deconvolved or forward modelled. By fitting observed profiles with synthetic profiles that include these broadening sources, observers extract estimates of temperature, proxies, surface gravity proxies, and projected rotational speed expressed in words as the speed at the equator multiplied by the sine of the inclination. Composition follows from which lines are present and how strong they are relative to one another. In a hot star, ionized helium lines can become prominent, while neutral hydrogen lines weaken, signaling a different surface mixture than in a hydrogen-dominated star of similar temperature. Ratios of lines from different ionization stages of the same element provide a handle on temperature because they respond to the balance between ionization and recombination. Ratios of lines from different elements provide abundance information when modelled, with atmospheres at the inferred temperature and gravity. Medium-resolution spectra can outline the broad picture by showing which sets of lines dominate. High-resolution spectra can refine abundance estimates by isolating weak features that sit between stronger lines. Both resolutions are useful, and both are often used in sequence with medium-resolution screening targets for detailed follow-up and high-resolution providing the fine measurements. Photometry complements spectroscopy by measuring the star's brightness in defined wavelength bands over time. Broadband colors, which are differences between magnitudes in two bands written in words, outline the overall shape of the spectrum from which rough temperatures and reddening by dust can be inferred. Time series photometry can reveal small changes in brightness that hint at pulsation spots, or residual orbital modulation if a companion once influenced the star. For motion studies, photometry can also measure how the centroid of the star's light shifts on the detector, with exposure time helping to diagnose tiny systematics in astrometry, that influence proper motion. In the halo, where extinction is low, photometric colors are closer to their unreddened values, simplifying the step from color to temperature proxy. Spectroscopic and photometric observations are planned to avoid contamination by Earth's atmosphere as much as possible. The atmosphere leaves absorption bands called telluric features, mostly from water vapor and oxygen. These features can mimic stellar lines if not corrected. Observers divide by spectra of hot feature-poor standard stars taken at similar air mass, or use models of the telluric transmission to remove these bands. Wavelength regions heavily affected by telluric absorption are treated with caution, and radial velocity work often favors windows where telluric contamination is weak. Instruments with stabilized environments and precise calibration sources reduce drift to very small levels. Laser frequency combs give a grid of lines at fixed intervals with absolute accuracy. Iodine cells imprint a stable forest of lines directly on the star's light for simultaneous calibration. Fiber feeds scramble the input light to make illumination of the spectrograph more uniform and stable. These engineering choices control instrumental systematics so that small shifts in line positions reflect true stellar motion. Repeated observations at different times test for changes in radial velocity. A stable velocity over many epochs supports the view that the star moves alone. Large changes suggest a companion and call for an orbital model. For a fast object in the halo that appears single consistency of radial velocity after corrections within the estimated error bars strengthens confidence in the derived space motion. If small variations appear, they must be compared with the measurement precision and with known instrumental patterns before assigning physical meaning. The final data products of this layer are a calibrated spectrum or set of spectra with measured line positions, depths and widths, a radial velocity with an uncertainty, a measure of projected rotational speed with an uncertainty, a set of abundance indicators from line ratios, and a photometric record that defines colors and any detected variability. Each quantity carries an error budget that includes photon noise, calibration uncertainties, model assumptions in profile fitting, and residual systematics. In a sparse halo field, those systematics are often smaller than in crowded disk fields because overlapping sources and variable extinction are reduced. Cross-checks between instruments and between nights hedge against hidden biases. When two independent spectrographs produce consistent radial velocities within errors, and when photometric colors agree with the spectroscopically inferred temperature, proxy internal coherence improves. All of these steps take place within the observation layer without naming a class or committing to an origin. These spectra provide motion along the line of sight and the ingredients for a description of the outer layers of the star in plain physical terms. The photometry provides the broad energy distribution and any time variability that might affect interpretation. Together they define what the data say about how the star moves toward or away from the observer, how quickly it spins in projection, what kinds of atoms and ions leave marks in its light, and how bright it is through selected windows, all expressed through measurements that can be repeated and checked. Within the observation layer, the spectrum and photometry together point to a clear stellar identity. The object is a hot helium-rich subdwarf of the O class. A subdwarf is a compact strip star that is smaller and less luminous than a normal star of the same surface temperature, and it shows high surface gravity. In this case, the spectrum displays strong helium lines in neutral and ionized states, and comparatively weak hydrogen features, which signals that the visible surface is dominated by helium rather than hydrogen. The overall energy distribution is blue and rises toward shorter wavelengths, consistent with a very hot surface that emits most of its light in the ultraviolet. Medium and high-resolution spectra define line shapes that fit models with high gravity and rapid rotation, and the absence of deep broad hydrogen series lines reinforces the helium-rich picture. Surface temperature read in plain words from the balance of helium ionization lines, and the weak hydrogen contribution lies in the range of many tens of thousands of degrees. At such temperature, atoms at the surface are largely stripped of electrons, and the prominent features come from helium at different stages of ionization. This temperature does not describe the core. It describes the thin radiating layer that is visible to telescopes. The high temperature explains the blue colors and the strong ultraviolet output, even though the star is physically small. Surface gravity inferred from the widths of pressure-sensitive lines and from fits to the overall profile of helium features is very large compared with the typical main sequence star. In simple terms, gravity at the surface is thousands to tens of thousands of times stronger than at Earth's surface. High gravity means the star's radius is small for its mass, so the light-emitting layer is tightly bound and produces narrow scale heights in the atmosphere. This high gravity leaves a mark in the wings of spectral lines which broaden under pressure. Models that include pressure broadening match the observed profiles when gravity is set to these high values, and the same models reproduce the continuum shape when paired with the high temperature indicated by the helium line ratios. Rotation is fast. The rounded shallow line profiles yield a projected rotational speed that is well above 100 km per second. Projected rotational speed is the equatorial spin speed multiplied by the sine of the unknown inclination angle. Because the inclination is not known, the reported number is a lower bound on the true equatorial spin. Even as a lower bound, a value above 100 km per second is large for a compact hot subdwarf. The rotation affects the spectrum by smearing each line over a range of wavelengths as parts of the surface move toward and away from the observer. The smearing is symmetric when other asymmetries are small, and the resulting profile has a characteristic shape that model spectra can fit to extract the projected speed. Photometry supports this picture by showing colors that align with a very hot emitter, and by showing no large periodic brightness, changes that would signal an eclipsing companion or strong surface inhomogeneities. Small variations, if any, remain within the measurement noise for the cadence and precision used. The lack of large photometric modulation is consistent with a single, compact, rapidly spinning star whose light is steady on the timescales probed, and it places limits on any residual structures on the surface that might modulate brightness as the star rotates. The classification as a hot helium-rich subdwarf also carries simple geometric implications for size and luminosity when compared with normal O-type stars. A normal O-type star with a temperature of many tens of thousands of degrees would be very large and extremely luminous. A helium-rich subdwarf with a similar surface temperature is much smaller in radius and radiates much less total power despite its hot surface. The high gravity derived from the spectrum encodes this small radius. A compact star with a radius of only a small fraction of the Sun's radius can still present a very hot surface and thus a blue spectrum while remaining far less luminous than a normal giant or main sequence O star. The combination of hot surface high gravity and helium-dominated spectrum is the defining signature of this class. Abundances beyond helium leave fainter marks but can be sketched in broad terms. Metals in stellar language, which means elements heavier than helium, appear at low levels. Some lines from nitrogen and other light metals can be identified, and their relative strengths to helium features suggest a composition that differs from that of the Sun. The exact pattern requires detailed modelling with non-local thermodynamic equilibrium atmospheres appropriate to such hot compact stars, but the broad outcome remains simple. helium dominates the surface. Hydrogen is depleted and heavier elements are present at low levels. This chemical portrait is encoded directly in which lines appear and how strong they are after accounting for temperature and gravity. Mass can be discussed only in cautious model-tied terms at this layer. Hot helium subdwarfs often cluster around a mass that is less than the Sun's mass when analysed through evolutionary tracks that pass through the observed temperature and gravity. Without invoking any particular path, one can say in plain words that a compact star with such gravity and such a small radius tends to have a mass of order, a fraction of the Sun's mass rather than many times the Sun's mass. This follows from the high gravity for a small emitting surface. Radius likewise remains in the small category when compared to main sequence or giant stars at similar temperature. Both traits are consistent with the line profiles and with the overall brightness once distance is considered. The atmosphere models used to match the spectrum assume a thin plane parallel layer held by strong gravity and heated from below by the star's interior. In that layer, helium provides the main opacity and line blanketing by metals, though weak shapes the continuum in subtle ways. The success of these models in reproducing both line depths and the overall shape across different wavelength ranges gives confidence that the temperature and gravity estimates are reliable within their stated uncertainties. The fit quality is checked by comparing multiple helium lines, by testing different microturbulence values that broaden lines on small scales, and by ensuring that independent high-resolution spectra yield consistent parameters. The lack of deep hydrogen features stands out in every spectrum. Hydrogen lines that would be strong in a normal hot star are shallow or absent here. This absence is not due to low temperature, since the continuum and helium features both indicate a very hot surface. It is due to low hydrogen abundance at the visible surface. The helium lines by contrast are strong, and at this temperature include both neutral and ionized states. Their relative strengths respond to temperature in a predictable way, and the measured ratios land in the range expected for a surface tens of thousands of degrees hot. The projected rotational broadening is measured by comparing the detailed shapes of several helium lines to rotationally broadened templates convolved with the instrumental profile. A single value fits many lines, which argues that rotational smearing rather than unresolved blends or pulsation dominates the observed widths beyond pressure and thermal broadening. Putting these observables together yields a coherent data-driven description. The star is compact and hot, with a helium-dominated atmosphere, high surface gravity, and rapid spin in projection. Its light is steady at the precision reached by the available time series. Its spectrum carries the hallmarks of a small, hot, high-gravity object that radiates strongly in the blue and ultraviolet, but with total power well below that of a normal O-type giant because of its small radius. Each component of this picture flows from direct measurements of line positions, line shapes, and broadband colors, and the resulting identity does not require assumptions beyond those needed to interpret spectra of hot compact stars under high gravity. Two broad families of ejection models are considered for a star that moves faster than the Milky Way's local escape speed. One family invokes strong three-body interactions near a massive black hole. The other family invokes the unbinding of a very close binary when a thermonuclear supernova disrupts the compact primary. Both families can in principle launch a star to extreme speed. The task is to compare their generic predictions with the measured kinematics and the measured stellar identity of a hot helium-rich subdwarf. In the massive black hole route, a binary star wanders into the deep gravitational well around Sagittarius A star. Tidal forces separate the pair. One component is captured onto a tight orbit around the black hole, and the other is flung outward at great speed. This Hill's mechanism produces high velocities that can exceed local escape speeds near the galactic center. It also imprints a preferred point of origin near the very center, and tends to eject stars that start as ordinary hydrogen-dominated stars because the binaries on lost cone orbits are drawn from the surrounding nuclear population. The predicted ejection directions are roughly isotropic around the center when averaged over many events, and the ages and compositions of ejected stars should broadly resemble those of stars that move in the inner bulge. In the donor remnant route, the starting point is a compact binary in the disk or halo in which a carbon-oxygen white dwarf accretes helium from a stripped helium star on an orbit with a period measured in minutes to hours in words. When the accreted helium layer or the white dwarf core ignites and a thermonuclear supernova occurs, the gravitational mass that binds the binary vanishes in a flash. The donor star, which had been moving at large orbital speed, continues almost freely on a straight trajectory, at a speed similar to its former orbital speed, possibly modified by a small kick. The donor survives as a hot helium-rich subdwarf that is rapidly rotating because tidal forces in the tight pre-explosion orbit had spun it up. This route does not prefer the galactic center, and can occur wherever compact binaries evolve to this state. Generic expectations from these two families can be set against the measurements. Trajectory first. A path traced backward in a smooth galactic potential from the present position and full space motion of the star lands not near the central parsecs, but in the outer disk or halo within uncertainties that reflect the measurement errors and the spread of plausible mass models. A galactic center launch is disfavored when the backward projection misses the nucleus by many thousands of light years even after uncertainties are accounted for. The three-body route near Sagittarius A star requires an origin very close to the center because the ejection speed scales with the tidal energy available there. A distant origin is not naturally produced by that route. Composition next. The observed spectrum shows a helium-dominated surface and weak hydrogen features. A Hill's mechanism ejection leaves the star's surface composition unchanged from its pre-encounter state, which for a typical nuclear cluster star would be hydrogen-dominated. It does not by itself remove a hydrogen envelope or build a helium-dominated surface. By contrast, the donor remnant route starts with a stripped helium star that is already helium-rich at the surface at the time of explosion. A surviving donor naturally presents a helium-dominated spectrum afterward. Rotation offers another comparison. The measured projected rotational speed is large for a compact hot subdwarf well above 100 km per second. Tidal locking in a very close pre-explosion binary predicts a fast spin at the moment the orbit vanishes with the equatorial speed set by the short orbital period and the small stellar radius. A surviving donor would thus carry rapid rotation forward. The Hill's mechanism does not predict rapid rotation as a generic outcome, because the ejected component could be any normal star with a wide range of spins, and the interaction changes the orbital motion rather than torquing the stellar surface strongly. Velocity amplitude is also diagnostic. The total speed relative to the galactic rest frame approaches values near 1,000 km per second, in round words, which is readily achieved in the donor remnant route because tight helium star plus white dwarf binaries have orbital speeds of that order. The Hill's route can also reach such speeds, but it requires the launch to occur in the deepest central potential, and the backtrace trajectory should then point to the nucleus. When the measured path does not align with the center, the black hole slingshot becomes an unlikely explanation for this specific object, even though it remains viable for other hypervelocity stars with center-pointing paths. The absence of a detected bound companion strengthens the donor remnant picture. After a thermonuclear supernova in a compact binary, the system unbinds and the donor departs alone. A residual companion would contradict the basic mechanism. A Hill's ejection can also send a single star away, but it leaves behind a captured companion near the black hole, rather than a distant partner alongside the ejector, which is not an observable signature tied to the moving star itself. Surface gravity and radius add context. A hot helium subdwarf shows very high gravity and a small radius. That state is the expected outcome for a stripped helium star that has been heated and slightly inflated by supernova impact, and that then relaxes back toward compactness on thermal timescales measured in millions of years in words. A Hill's ejector star would be whatever it was before the encounter, and would not naturally become a compact helium subdwarf unless it began as one which is not a typical product of the nuclear star cluster. Chemical detail offers minor but consistent traces. Light metal lines that hint at processed material at the surface can appear in helium subdwarfs that have lost their hydrogen envelope. Such patterns do not favor a galactic center ejection or a supernova donor uniquely on their own, but in combination with helium dominance they align with a history of stripping and prior mass transfer. The ensemble of traits that include helium-rich, surface-high gravity, rapid spin, and a path that does not trace back to Sagittarius A star are all expected at once in the donor remnant route, and are not all expected at once in the black hole route. Uncertainties remain. The measured rotational speed is a projection that depends on the unknown inclination. The exact back-traced path depends on the galactic potential adopted for the integration and on the present velocity errors. Spin evolution after the explosion may include angular momentum loss or redistribution in ways that change the surface rotation on million-year timescales. The degree to which supernova impact strips additional surface material or injects heat depends on the separation at explosion and on the ejector geometry, which are not directly observed. These uncertainties affect details within each family rather than the broad contrast between them. Population context helps guard against overinterpretation of a single case. Hypervelocity stars that are hydrogen-dominated and traceable back toward the center fit cleanly within the black hole route and populate that family. Helium-rich hot subdwarfs with large space speeds and paths that miss the center populate the donor remnant family. The two routes thus describe overlapping but distinguishable subpopulations when identity and trajectory are both considered. For an individual helium-rich hot subdwarf with very high speed, a backward path that avoids the center, and rapid spin, the donor remnant scenario, is the model family whose general expectations most closely match the measured traits. The black hole route remains a valid mechanism in general for other targets, but its characteristic origin point and generic stellar types do not align with the specific identity and trajectory observed here. The space that a fast star crosses in the galactic halo contains very little matter. Gas there is thin, hot, and mostly ionized with temperature of roughly 1 to 2 million degrees in words, and with densities far below 1 particle in a cubic centimeter. Dust grains are rare and small, and their integrated effect on starlight along a high latitude path is slight, compared with the effect inside the disk. Magnetic fields thread the halo at strengths that are weak compared with those near dense clouds, and the large-scale field varies smoothly over long distances. In this environment, the primary influence on the star's motion is gravity from the Milky Way's mass, while direct forces from gas and dust are too small to change the path by any measurable amount on the travel times considered. Drag in a gas depends on the density of the medium and the square of the relative speed. The star's relative speed is very large, but the density is so small that the product remains tiny. A compact star presents a small cross-section. Its outer layers are bound by very high surface gravity, and it does not carry an extended atmosphere that would couple strongly to the gas. The mean free path between particle collisions in the hot halo is long, and the flow around the star is in the regime where individual particle interactions matter more than continuous fluid behavior on small scales. Under these conditions, ram pressure acts only on a minuscule area and produces a deceleration that is negligible compared with gravitational acceleration from the galaxy. Estimates cast in words show that the time it would take for such drag to change the speed by a modest fraction is longer than the time that the star spends in the halo by wide margins. Accretion from the halo gas is likewise very weak. The rate at which material is gravitationally gathered from a diffuse medium by a moving compact object scales with gas density and with the square of an effective sound speed plus the square of the relative speed. In the hot halo, sound speed is high and relative speed is higher still, so the effective capture radius is tiny. The resulting mass intake per unit time is extremely small, and the total mass gained over long travel is negligible compared with the mass of the star. Any astrophysical impact from such weak accretion, such as a detectable change in surface composition or a luminous wake, remains far below present measurement limits in this environment. A fast star can in principle drive a bow shock where its motion compresses the gas ahead, but the faint halo does not provide enough material to light such a structure brightly. Shocked gas would emit little in optical lines, and far ultraviolet bands at the densities and temperatures expected. The scale of any shock would be small compared with the distance between stars, and the emission would blend into the diffuse background. The star's own wind, if present at all for a hot helium subdwarf, is weak. Mass loss rates for such compact high-gravity objects are low, and the wind momentum is too small to carve a large cavity in a hot rarefied medium at high relative speed. The astrosphere that would form is tiny and would not affect the kinematics of the star. Interactions with dust grains reduce further in the halo because grain abundance is low, and because high temperature sputters grains over long times. Extinction along the line of sight through the halo is mild, so color corrections for dust are small, and the path length needed to produce noticeable reddening is large. As a result, the observed colors of the star reflect its hot surface more directly than they would in a dusty inner disk field. That clarity helps temperature estimates and reduces one source of uncertainty in distance, estimates that rely on brightness and color. Magnetic fields in the halo contribute a pressure that is tiny compared with the ram pressure of a star moving at extreme speed, so magnetic drag is not a meaningful break. The alphen speed in the diffuse halo is low compared with the star's relative speed, so the motion is strongly superalphenic and does not excite large coherent magnetic structures that could sap kinetic energy. Small-scale plasma effects such as charge exchange between stellar wind ions and ambient gas, or the formation of a narrow contact discontinuity, occur only within a very small region around the star. Any radiation that results from these processes is confined and faint. Gravitational interactions with individual stars are effectively absent in the halo because the stellar density is low. The time between close encounters that could deflect or slow the object by a detectable amount is many orders of magnitude longer than the travel time across the region. Two-body relaxation, which slowly changes velocities in dense systems through many weak encounters, operates on timescales that exceed the age of the galaxy for such a low-density field. Passage near a globular cluster or a satellite stream is possible in angle, but the physical distance to their member stars remains large, and the integrated gravitational tug from such structures acts as part of the smooth potential rather than as discrete kicks. Dynamical friction, which is the drag that a massive object feels as it raises a wake in a sea of lighter bodies, is negligible for a single low-mass star in the halo because the effect scales with the square of the mass of the moving object and with the ambient density. The star's mass is small in galactic terms, and the halo density is low, so the wake is vanishingly weak and carries too little momentum to matter. Cosmic rays and background radiation fill the halo, but their pressure is tiny when compared with the kinetic energy density of a star moving at thousands of kilometers per second in words. The star's motion does not couple to this background in a way that would measurably change its speed or direction. Photons from the ultraviolet background and from the diffuse ionizing field can ionize trace material in any tiny wake, yet the amount of material is too small to feed back into dynamics. The thermal state of the halo gas means that the sound speed is a non-negligible fraction of the star's relative speed. But because the density is so low, compressibility effects do not translate into substantial momentum exchange. Any pressure waves launched ahead are faint and quickly dissipate. The star therefore moves in a near-ballistic way through a medium that offers almost no resistance. Small cold clouds do exist in the halo, including high-velocity clouds that carry neutral hydrogen at lower temperature. The filling factor of such clouds is low, and the chance of a direct crossing along a random long path is small. Even if a grazing passage occurred, the cloud's size and density would need to be large to produce a measurable drag impulse or to leave a bright compact emission. Nebula and such conditions are uncommon far from the disk. Observational records for similar fast compact stars rarely show strong, sharp nebulae in the halo, which aligns with the expectation that interactions with neutral clumps are rare and mostly weak. The gravitational field across the size of the star is effectively uniform because the star is small and the galactic potential varies only on kiloparsec scales. Tidal gradients across the stellar diameter are tiny, so internal tides raised by the galactic field do not deposit heat or alter rotation in any appreciable way. The only long-range effect of the halo environment on the star's light is a mild, slowly varying foreground that can be corrected by standard extinction maps, leaving the spectrum and colours largely set by the star itself. The local environment in short descriptive terms is a near vacuum, where the star's compact size, rapid speed and high gravity combine to decouple it from gas and dust. The measurable properties that define its motion and identity arise from internal structure and from the galaxy's smooth pull, not from ongoing exchange with surrounding matter. Time enters the description of a fast star in two complementary ways. One is kinematic time, the interval required for the star to move from a probable launch region to its present position under the gravity of the Milky Way. The other is stellar time, the set of internal clocks that govern how a compact hot, helium-rich subdwarf cools, spins and relaxes after any heating or stripping event. Both kinds of time can be estimated from measurements already in hand without adding new assumptions. Kinematic time is reconstructed by taking the present position and three-dimensional velocity of the star and following its path backward through a smooth model of the galactic gravitational field. The field is described by a potential that combines the disk, the central bulge, and the dark matter halo. With that potential fixed, the backward integration is a numerical solution of the equations of motion that steps the star to earlier positions and speeds while conserving energy and angular momentum to the accuracy of the integrator. Because the present position and velocity carry uncertainties, The calculation is repeated many times with inputs drawn from their allowed ranges. The outcome is an ensemble of past trajectories. Each trajectory intersects the galactic plane at one or more points as it rewinds, and the earliest crossing after the present corresponds to a time since last plane passage. If the ensemble of crossings accumulates in a broad patch of the outer disk, rather than at the nucleus, the launch region is placed there at an angle, and the time since launch is identified with the backward interval from that crossing to now. Gravity slows the star as it climbs outward from deeper parts of the potential, so the travel time is longer than the naive estimate obtained by dividing the present distance from the plane by the present speed. The integration accounts for this deceleration, and for small deflections caused by the non-spherical mass distribution. The typical outcome for a present speed near 1,000 km per second and a present distance measured in many tens of thousands of light years is a kinematic time of order, tens of millions of years in words, with a spread that reflects the velocity and distance errors and the family of acceptable galactic mass models. The quoted interval is an ensemble property rather than a single number. It describes a band of probable travel times that broaden when distance precision loosens, and that narrow when parallax and proper motion are tight. The backward calculation can also provide a time since last pericenter, if the trajectory curves around and reaches a closest approach to the galactic center in the past. But when the integrated path remains far from the center, the pericenter concept is not the relevant marker. Plane crossing is then the clean temporal landmark because it is well defined in the galactic coordinate frame and is tied to a specific geometric event. In parallel with kinematic time, stellar time unfolds in the compact star itself. After a stripping and heating episode, the surface layers cool, and the interior re-establishes a thermal gradient on a Kelvin-Helmholtz timescale that depends on the star's mass radius and luminosity. In plain words, this is the time it takes the star to radiate away its internal thermal energy at the current rate. For a compact high-gravity hot subdwarf with a radius that is a small fraction of the Sun's radius, and a luminosity well below that of a normal O-type star, this timescale tends to be measured in millions of years to some tens of millions of years. The observable consequence is that the surface temperature and gravity inferred from the spectrum describe a star that can remain hot over the same order of time as the kinematic travel from a probable launch site in the disk to the present halo location. Rotation evolves on its own clock. A very close pre-event orbit would have synchronized the donor's spin with the orbit, producing a rapid surface rotation at the moment the system unbound. Afterward, the absence of a companion removes the strong tidal torque, and the spin changes mainly through weak winds and through internal redistribution of angular momentum. Hot helium subdwarfs have low mass loss rates, so windbreaking is gentle. The timescale to reduce the rotation substantially by wind torque alone is long, compared with a few million years, and can approach or exceed tens of millions of years, depending on the adopted wind prescription. The measurement of a projected rotational speed well above 100 km per second is therefore consistent with a star that has had only limited time to slow. Diffusion and levitation in the atmosphere supply another clock. Under high gravity, heavier elements tend to sink, while radiation pressure can push selected ions upward. The competition sets surface abundances over time. The diffusion timescale in the thin hot atmosphere is short, compared with nuclear evolution times, often measured in thousands to hundreds of thousands of years in words, so the observed helium dominance at the surface does not require a long wait to appear and can persist as long as the atmosphere remains hot and thin. This timescale is much shorter than the kinematic travel time, which means the surface composition seen now is not a transient imprint that would have vanished en route. Cooling and structural evolution proceeds slowly compared with the diffusion cycle, so the surface remains helium-rich while the star moves through the halo. The nuclear timescale of a helium-burning core, if present, sets the ultimate lifetime of the current phase. For compact helium subdwarfs that sit at high gravity and high temperature core helium, burning or shell burning may continue for times of order a few tens of millions of years to perhaps 100 million years in broad terms, depending on mass and structure. This range overlaps the kinematic travel intervals implied by backward integration to a disk launch. The coexistence of a long nuclear timescale, a multi-million-year thermal timescale, and a multi-million-year halo flight time explains in plain terms why a hot, compact, helium-rich star can be observed far from the disk while still hot and rapidly spinning. Each clock allows that circumstance without strain. Uncertainties in each timescale can be described without invoking details that lie beyond current measurements. The kinematic interval broadens when the distance error increases because transverse speed scales with distance. It also broadens when the radial velocity error increases because that component often dominates the total speed budget. The spread in accepted galactic potentials shifts travel times by the amount needed to reflect different halo concentrations and disk masses. These shifts are modest when all models fit the same ensemble of tracers. The thermal relaxation time depends on uncertain opacities and on whether additional heat was injected into the outer layers at launch. But even a reasonable range of such inputs keeps the answer in the multi-million-year band. The spin-down time hinges on wind prescriptions and on the internal coupling between core and envelope. A conservative reading of compact hot subdwarf physics still yields a breaking time that is not short compared with the flight time. Diffusion times depend on surface gravity and temperature that are already constrained by spectra. At the measured high gravity and high temperature settling, and levitation operate quickly enough to set the surface pattern early and maintain it. A simple cross-check ties the clocks together. If the backward integration places the last disk crossing at a time measured in a few tens of millions of years, and the star's surface remains at a temperature of many tens of thousands of degrees with high gravity today, then the thermal clock must allow sustained heat over that span. The observed blue colors and strong helium lines confirm that allowance. If the projected rotational speed remains large now, then the breaking clock must not have had time to erase the initial spin. The weak wind of a compact high-gravity star satisfies that condition. If diffusion acts quickly, then the helium dominance need not be primordial at the instant of launch to be present now. It can be re-established early along the route and kept in place. With these estimates, time becomes a descriptive axis rather than a speculative one. The past travel is measured by backward motion. In a known field, the present state is read from spectra and photometry, and the internal clocks operate at rates that are consistent with both. The star's age as a helium subdwarf phase can be of the same order as the time since it left the disk, while the much longer times associated with global galactic evolution remain irrelevant at this scale. The convergence of kinematic and stellar timescales removes the need for special pleading. The star can be where it is, and as it is because the relevant clocks all run at speeds that agree with the measured motion and identity. Fate for a fast compact star is governed by gravity on the larger scales and by internal evolution on the smallest. In the galactic frame, a present speed above the local escape threshold sets the path as an open curve that does not close on itself. The star recedes through the outer halo slows as it climbs the Milky Way's potential well and approaches an asymptotic speed far from the galaxy where the gravitational pull becomes weak. The shape in simple terms is a broad hyperbolic-like trajectory relative to the Milky Way's center, though in practice the curve is gently deflected by the flattened disk and the extended dark halo. As distance grows to many hundreds of thousands of light-years in words, the deceleration declines, and the star's velocity tends toward a constant value that is lower than the present speed but still substantial. The local environment remains sparse. The circumgalactic medium thins further outward, and the probability of a close stellar encounter drops from already negligible to essentially zero. Gas drag remains ineffective, and dynamical friction remains vanishingly small for a single low-mass star. The star's motion is therefore set almost entirely by the integrated gravity of large structures, rather than by local interactions. Once beyond the region where the Milky Way's mass dominates the background field, transitions to the combined pull of the local group. The principal masses are the Milky Way and the Andromeda Galaxy, with their extended dark halos plus smaller contributions from satellite galaxies and diffuse matter. The star's path with respect to the Milky Way continues outward, but its motion with respect to the local group depends on its direction and speed relative to the group's rest frame. If the speed remains below the escape threshold of the local group potential in the star's direction, the path will bend slightly under the combined pull and asymptote to a broad orbit around the group center of mass, becoming part of the intragroup stellar population. If the speed and direction place it above that group scale threshold, the path will continue past the group's influence and approach the general flow of nearby structures. The assessment rests on the same local comparison used within the galaxy, extended to a larger mass distribution. In either case, the change in course is gradual spread, over times measured in many billions of years in words, and there is no sharp boundary crossing. From the perspective of observers tied to the Milky Way, the star's observable properties evolve smoothly with distance. Angular proper motion declines as the star recedes because the same space speed corresponds to a smaller angle per year. When the separation grows, parallax shrinks towards zero, reducing distance precision available to any observer who follows with a parallax method. Apparent brightness decreases with the square of the distance, so the star becomes fainter at a predictable rate in the absence of strong extinction changes which the halo and intergroup space do not supply. Radial velocity measured in the solar system frame approaches a constant, as the Sun's own orbital contribution becomes a small correction compared with the long baseline motion. Spectral features remain the same in kind, but their signal weakens with flux. The future dynamical relation to the Andromeda Galaxy involves an additional gentle influence because Andromeda and the Milky Way move toward each other on a long time scale. The star's path is integrated through a potential in which both halos evolve, but the slow change means that on the scale of a few 100 million years to a few billion years in words, the dominant effect remains the current mass distribution. The possibility of capture by Andromeda or by a satellite system arises only if the trajectory passes sufficiently near those masses with the speed below their local escape thresholds, which is not typical for a star that left the Milky Way at extreme speed and did not aim directly toward another deep well. Most such paths remain as wide passes through the group field. Internal evolution proceeds in parallel without strong coupling to the large-scale dynamics. A hot helium-rich subdwarf exhausts its current nuclear fuel over times measured in many tens of millions of years to perhaps around 100 million years, depending on mass and structure stated in broad terms. As helium burning wanes, the star contracts and cools toward a white dwarf state, with a mass that is a fraction of the Sun's mass. The surface temperature, now high, will slowly decline over much longer times as the object radiates its residual heat. Rotation, initially rapid, will decrease gradually through weak wind torques and internal redistribution. The projected rotational speed that is measured today will drop over hundreds of millions of years and longer, but the spin will not vanish quickly because the braking mechanisms are weak in such compact high-gravity stars. Surface abundances will reflect the ongoing balance of diffusion and radiative levitation as the temperature and gravity evolve. Helium dominance at the surface can persist while the atmosphere remains hot and thin with heavy elements settling, and selected ions levitated according to line opacities. As the object cools toward a white dwarf, the atmosphere structure changes and diffusion patterns adjust accordingly, eventually settling into the stratified layers characteristic of white dwarfs. Throughout this internal evolution, the star remains dynamically small and offers little cross-section to the tenuous gas of intergroup space, so external accretion does not modify the course. The cooling white dwarf stage extends for times that dwarf the travel time across the local group. Over billions of years in words, the star dims steadily shifting its peak emission from the ultraviolet through the optical and into the infrared as temperature falls. For an external observer who tracks its path in a coherent group frame, the moving point source that once shone blue and hot will become a faint redder ember on a long outbound track or a broad intragroup orbit depending on the group scale binding. The distinction carries no consequence for the internal cooling which is set by the star's stored heat and radiative loss. Gravitational microlensing events caused by the star as it passes in front of more distant sources remain possible in principle, yet the chance alignment required is rare in such empty regions, and any such events would be brief and faint given the small mass and the low surface density of background stars in intergroup directions. Magnetic braking through interaction with a background field is negligible, because the field is weak and the coupling cross-section is tiny. Tidal heating by the group potential is absent, because the potential varies on scales many orders of magnitude larger than the stellar diameter. The fate therefore reduces to a near ballistic escape from the Milky Way, a gentle deflection by the smooth field of the local group, and a long cooling track from a hot helium subdwarf to a white dwarf and onward to ever lower temperature. The timescales that control brightness and colour changes are far longer than those that carried the star from the disk through the halo. The dynamic and thermal evolutions proceed together, but without significant interaction. The trajectory continues outward with small curvature set by diffuse mass, while the interior runs down its nuclear and thermal reservoirs in a predictable sequence for a compact helium-dominated remnant. Observers in future epochs will find the object dimmer, slower in angular drift and cooler, yet still carrying the same conserved momentum that launched it, altered only by the broad, slow pull of the surrounding mass distribution. Frames of reference turn raw measurements into motion with respect to the Milky Way. The telescope records angles on the sky, changes of those angles with time and a shift of spectral lines. These belong first to the observer's frame which sits on Earth and rides around the Sun while the Sun orbits within the galaxy. To compare a star's speed with the local escape speed of the Milky Way, the motion must be expressed in a galactic rest frame that removes the observer's own movement and the bulk rotation of the disk. The steps are orderly, and each has a clear physical meaning. The starting point is the solar system barycentric frame. Radial velocities are corrected to this frame by removing Earth's daily rotation and yearly revolution, so the shift of the star's lines reflects motion along the line that joins the Sun and the star at the time of observation. Proper motions are tied to a fixed sky grid anchored to distant galaxies, so that the slow drift on the sphere is not biased by instrument flexure or seasonal parallax. Distances from parallax or photometry complete the set. With these in hand, the three components of velocity in the barocentric frame are built one along the line of sight, and two in the plane of the sky, aligned with increasing galactic longitude and latitude. The next correction removes the Sun's own peculiar motion relative to the average motion of nearby disk stars. In plain words, the Sun moves a little faster or slower than the disk, and a little up or down with respect to the plane. This small offset is described by three numbers along the axes that point toward the galactic center, along the direction of disk rotation, and toward the north galactic pole. Subtracting this vector shifts the velocity from the solar peculiar frame to the local standard of rest, which is a notional frame that co-rotates with the disk at the Sun's radius. This step matters because a star's speed measured against the Sun mixes the star's true galactic motion with the Sun's private drift. Removing the drift isolates the part that belongs to the star alone in a frame that turns with the local disk. The disk itself rotates around the galactic center at a speed set by the mass distribution interior to the Sun's orbit. That mean rotation must also be removed to create a non-rotating galactic rest frame. In practice, the transformation moves from the local standard of rest to a galactocentric frame whose origin is at the galactic center and whose axes are fixed in space. The component of velocity that lies along the direction of disk rotation is adjusted by the local circular speed, and the position of the star is placed in a three-dimensional Cartesian system centered on the Milky Way's center. The result is a velocity vector that tells how the star moves with respect to a frame in which the bulk of the disk is not swirling past. The magnitude of this vector is the speed used when the label bound or unbound is assigned, because the escape threshold is defined in the same central frame. Care is taken with signs and directions so that outward motion from the center is recorded as positive along the radial axis, and motion toward the north galactic pole is recorded as positive along the vertical axis. This construction uses only words and geometry. No equations are needed beyond the idea that velocities add and subtract like arrows. Each correction removes a known arrow that belongs to the observer or to the rotating disk. Each remaining arrow belongs to the star's actual flight through the Milky Way. The accuracy of the final speed depends on the accuracy of every input arrow. Uncertainties in proper motion distance and radial velocity propagate through the subtractions and rotations. The Sun's peculiar motion and the local circular speed are known with finite precision, so they contribute small shared uncertainties to all transformed velocities. To capture these effects, honestly observers repeat the transformation many times with inputs drawn from their measured error ranges. The outcome is not a single speed, but a distribution of speeds in the galactic rest frame from which a most likely value and a confidence band are quoted. When the distribution sits well above the escape threshold in common mass models, the classification as unbound is robust. When it straddles the threshold, the answer depends on which mass model and which part of the speed distribution one adopts. The frame construction also clarifies the split between radial and tangential components in the galactocentric sense. The star's velocity can be expressed as a part that points directly outward from the center, a part that lies along the direction of disk rotation, and a part that points toward the north galactic pole. These three numbers tell whether the star is climbing mainly outward, skimming around the center, or moving strongly above or below the plane. For a hypervelocity helium subdwarf, the outward component is typically very large and positive. The rotational component can be small or even opposite in sign to the local disk rotation, and the vertical component can be significant if the path crosses the plane at a steep angle. This split has descriptive value because it ties motion directly to the shape of the Milky Way's gravitational well-outward motion fights. The main pull, Rotational motion reflects angular momentum about the center, and vertical motion shows how quickly the star departs from or approaches the plane. Transformations between frames also require a choice of the Sun's distance from the galactic center. That distance enters when placing the Sun and the star in the galactocentric coordinate system. Reasonable changes within the accepted range shift the derived position and the decomposition of the velocity by small amounts. The final speed is less sensitive than the individual components because speed depends on the sum of squares of components in words which averages small shifts. Even so, the adopted distance and circular speed are recorded with each analysis, so that results can be compared fairly across studies. A related detail is the definition of the galactic coordinate axes. The zero of longitude, the position of the North Galactic Pole, and the transformation from equatorial coordinates to galactic coordinates follow an International Astronomical Union standard. Using a consistent standard ensures that longitudes and latitudes match across catalogues, and that the direction of each velocity component is the same from one dataset to another. Modern astrometric catalogues tie their reference frames to distant quasars, which keeps the axes fixed with respect to the distant universe and reduces rotational drift of the grid. After the transformation, the final quantity compared with the escape threshold is the speed in the non-rotating galactocentric frame. The threshold itself is computed from the galactic potential used in orbit integrations. It is a function of position, so the star's current galactocentric radius and height above or below the plane are used to evaluate it. Because both the speed and the threshold carry uncertainties, the comparison is made over their ranges. The fraction of trials in which the speed exceeds the threshold provides a direct statement of how confidently the object is classified as unbound within the chosen family of potentials. This probabilistic phrasing respects the limits of the data and the model, and avoids overstatement when a star lies near the boundary. Frames also shape the presentation of the measured motion. In the observer's frame, a very far star can still have a modest proper motion if it lies far away, because angular drift scales inversely with distance. In the galactocentric frame, the same star can have a very large outward component even if the proper motion appears small to a telescope on Earth. Conversely, a large proper motion at small distance can correspond to a moderate galactocentric speed if most of the motion is a sideways glide that does not add strongly to outward climb. Reporting both the heliocentric observables and the galactocentric components closes this loop by connecting what is seen at the telescope to what is relevant for binding. Each step in the chain from raw angles and wavelengths to a galactic rest frame speed has checks. Independent spectrographs should yield the same barycentric radial velocity within errors. Independent reductions of proper motion from different time baselines should agree on drift direction. Transformations performed with different adopted values of the Sun's peculiar motion and circular speed should alter the final answer by amounts consistent with their known uncertainties. When these checks pass, the final velocity, relative to the galactic rest frame, stands on a stable base, and the labels bound or unbound follow from a local comparison made in the correct frame for the Milky Way. Distance anchors every derived speed, and the route to distance for a compact hot helium-rich subdwarf in the halo proceeds along two complementary channels that can be checked against each other. The geometric channel is parallax, the tiny yearly wobble of apparent position as Earth circles the Sun. The photometric channel is standard candle reasoning, which compares observed brightness and colour to model atmospheres that predict intrinsic brightness for a star with the measured temperature and gravity. In the halo, where extinction by dust is small along high latitude lines of sight, Both channels work cleanly, and each has a distinct error budget that can be quantified. Parallax converts an angle written in tiny fractions of a degree into a distance by simple geometry. The angle is small because the baseline, the diameter of Earth's orbit, is finite while the stars are far. Measuring such angles requires a stable reference frame tied to distant galaxies and repeated observations over many seasons to separate true annual wobble from straight-line proper motion. The fit includes 3 ingredients at once: a linear drift for proper motion, a sinusoidal term for parallax with known phase set by Earth's path, and small instrument offsets that reflect detector geometry. The parallax amplitude then yields a direct distance. Random errors arise from photon noise and from centroiding uncertainty on the star's point spread function. Systematic errors enter through small rotations or scale changes of the reference frame and through color-dependent shifts in the optics. These are assessed by comparing many stars in the same field and by testing for correlations with observation geometry. A robust parallax solution publishes not only a best value, but also an uncertainty that mixes random and systematic contributions in words. Photometric distance begins with a calibrated spectrum that fixes temperature and gravity through helium line ratios and pressure-broadened wings. A model atmosphere for a hot high-gravity helium-dominated surface then yields the absolute brightness in selected bands for that pair of parameters. Observed brightnesses in the same bands corrected for small dust reddening along the line of sight using all sky extinction maps give the difference between absolute and apparent levels, which is the distance modulus stated in words. The corrections for dust are small at high latitude but not zero. They are tested by checking colours across multiple bands and by comparing with neighbouring sightlines. Uncertainties come from flux calibration errors from the spread of models at the measured parameters from any residual reddening uncertainty, and from the possibility that the star's atmosphere departs modestly from the idealized grid used. When both channels are available, comparison is straightforward. Agreement within quoted errors increases confidence that no hidden bias dominates. A small tension can be studied by asking which inputs contribute the most to the discrepancy: a slight 0-point shift in parallax, a modest change in the adopted reddening, or a narrow range in temperature and gravity that still fits the spectra. Because transverse speed scales linearly with distance, even a small fractional change in distance shifts the sideways kilometers per second by the same fraction. The total space speed, which combines transverse and radial parts, then moves accordingly. Error propagation begins by sampling the parallax or the photometric distance within its uncertainty, the proper motion components within theirs, and the radial velocity within its quoted error. Each sampled set is transformed into the galactic rest frame, using the adopted solar motion and circular speed values. Thousands of such trials form a cloud of possible 3-dimensional velocities at the present position. From that cloud, the distribution of speeds and the split into radial, rotational, and vertical components are read directly. The method captures asymmetries in the errors, such as a larger positive uncertainty in distance than negative due to parallax inversion, and it carries shared systematics such as the uncertainty in the sun's circular speed through every trial. The result is a statement in words like most probable speed with a range that encloses a chosen fraction of trials. Systematic checks accompany the numbers. Independent astrometric reductions over different time baselines should agree on proper motion within errors. Any field-dependent drift would show up as a pattern in residuals when positions are referenced to distant galaxies. Independent spectrographs should agree on barocentric radial velocity within calibration precision. A drift with time would hint at an unseen companion and would broaden the allowed radial range in the trials. Independent extinction maps and color excess estimates should agree at high latitude to within small fractions of a magnitude in words. A larger discrepancy would flag caution on the photometric distance. Model atmosphere dependence is probed by fitting spectra with different line lists, different microturbulence parameters, and different helium-metal mixtures. The spread in the derived absolute brightness across these grids becomes part of the photometric distance error. For a helium-dominated subdwarf at very high temperature and gravity, the model families used by observers converge closely because helium lines are strong, and pressure broadening is well constrained, yet the small residual spread is retained. The parallax solution includes a quality metric that reports whether the star's image behaves like a stable point source. A high metric and low residuals support the interpretation that the parallax and proper motion fits are not confused by blending with a neighbour. In the sparse halo, blending is uncommon, but the check is performed regardless. Saturation at very high brightness or very rapid drift across the detector can degrade fits. Neither applies in typical cases for hot subdwarfs at halo distances, which occupy a mid-range where images are clean and angular. Drift per year is small enough to keep the source within a stable point spread footprint. Small color terms arise because the optics and detectors are not perfectly achromatic. If calibration stars differ strongly in color from the target, tiny biases can creep into position measurements. This is tested by selecting a calibration set that spans the color of the target, and by applying color-dependent corrections derived from the ensemble. For a very blue star, the calibration set must include similarly blue objects. Surveys that cover the sky contain enough such stars that the requirement is met. Once distance is set, the star's absolute magnitude and thus its luminosity follow, and with an effective temperature from the spectrum, a radius estimate emerges through the relation between luminosity radius and temperature stated in words. That radius, combined with the measured high gravity, provides a simple mass estimate that lies in the fraction of a solar mass range expected for compact helium subdwarfs. The internal consistency among radius, mass, gravity, and luminosity acts as a further check on the adopted distance. If parallax and photometry disagree sharply, the inferred radius or mass would contradict the spectral gravity. Such a mismatch signals that one of the inputs needs revision. In favourable cases, parallax provides the primary distance, and photometry serves as a cross-check. In cases where parallax precision is modest because the star lies far, and the parallax angle approaches the noise floor, photometry anchors the distance, while parallax supplies a loose prior that prevents the brightness solution from drifting into implausible ranges. The combination of both is stronger than either alone. With distance in hand, the computation of transverse kilometers per second from proper motion takes a single step in words: angular drift per year, multiplied by physical scale per unit angle at the measured distance. Expressed this way, the dependence on distance is transparent, and the sensitivity of speed to fractional changes in distance is easy to visualize. A 10% increase in distance raises transverse speed by 10%. A 10% decrease lowers it by the same amount. Radial velocity remains untouched by distance, so the total speed moves less than the transverse part unless the transverse dominates. Reporting the fractional contributions of transverse and radial parts clarifies how distance uncertainty maps into total speed uncertainty. The final product of this distance-focused layer is a coherent set of numbers at distance with an uncertainty that reflects both parallax and photometric inputs, a luminosity and radius consistent with the spectral gravity, a transverse speed with the distance-driven error bar, and a total galactic rest frame speed with a full propagated uncertainty. Each number is tied to direct observables and to cross-checked calibrations suited to a hot helium-rich compact star in a sparse halo field. Every measurement that builds the motion of a fast halo star arrives with uncertainty, and the character of those uncertainties matters as much as their size. Proper motion is a fit to positions recorded at many epochs. Each position is a centroid derived from a point spread function sampled by pixels with small sensitivity variations. Random noise from photon statistics makes the centroid wander slightly, while systematics from optical distortions, thermal flexure, and color-dependent refraction can shift it in a preferred direction if uncorrected. The mitigation is to anchor all epochs to a reference frame defined by distant galaxies, to linearize detector geometry, and to model color terms with calibration stars that bracket the target's blue color. The proper motion fit then returns a slope with an error that reflects both scatter and systematics. The error is anisotropic when the time sampling is uneven, or when one coordinate is more stable than the other. This sky plane uncertainty becomes an ellipse rather than a circle, and this ellipse maps to a band of directions for the great circle of motion. Radial velocity is the average shift of many spectral lines relative to laboratory wavelengths. Random error arises from finite signal to noise per pixel, from blends that alter line cores, and from telluric residuals where Earth's atmosphere imprints its own lines. Systematic error enters through wavelength calibration, drift between exposures, spectrograph flexure over a night, and template mismatch if the stellar atmosphere used to define line centers differs subtly from the actual one. To limit these observers, use simultaneous calibration sources, stabilize spectrographs thermally, and avoid wavelength ranges with strong telluric bands. Repeating the measurement on different nights and with different instruments provides an external check. Agreement within quoted errors argues that hidden biases are small. Distance contributes a distinctive uncertainty because transverse speed scales linearly with it, while radial speed does not. Parallax solutions carry random error from centroiding, and systematic error from reference frame imperfections and attitude modeling of the satellite that gathers the data. The inversion from parallax angle to distance is non-linear. A symmetric error in parallax produces an asymmetric error in distance. Analyses therefore perform the propagation by sampling parallax in its native units, converting each draw to distance and combining with proper motion in that draw. Photometric distances depend on model atmospheres. Uncertainties in temperature, gravity, and helium metal mixture translate into a small spread in predicted absolute brightness. Reddening corrections at high latitude are small but not zero. Dust maps place bounds and multiband colors test consistency. When parallax and photometric estimates are combined, the joint distance is taken as a weighted distribution that reflects both channels. The Sun's peculiar motion and the local circular speed introduce shared uncertainties that are common to all stars transformed into a galactic rest frame. The peculiar motion is known to within a few kilometers per second in each component written in words. The circular speed is known to within a few tens of kilometers per second. These numbers shift the derived galactocentric components coherently. Analyses propagate them by sampling from their allowed ranges along with the star's observables, so that the final speed distribution widens appropriately. The galactic potential used to compute escape speed and to integrate past or future paths also carries uncertainty. Disk mass, bulge profile, and halo concentration each alter the depth and shape of the potential well. Families of acceptable models are constrained by rotation curves, satellite motions, and stream fits, yet they differ within those bounds. For a given position, different models yield slightly different local escape speeds. The classification of a star as unbound is therefore probabilistic. The fraction of trials drawn from the observable errors and the model family for which the speed exceeds the local escape speed is the reported confidence. When that fraction sits near unity across model families, the label is firm. When it sits near 1/2, the label is uncertain and sensitive to assumptions. Correlations between errors require attention. Proper motion components can be correlated if the astrometric solution couples the two coordinates. Parallax can be correlated with proper motion if the time sampling confounds annual wobble and linear drift. Spectroscopic systematics can correlate radial velocity with projected rotational speed if line broadening biases centroids. Modern catalogues report covariance matrices for astrometry. Analyses draw samples from the full covariance to preserve these correlations. Spectroscopic pipelines test for velocity shifts as a function of line width to detect any coupling. These steps prevent underestimation of uncertainty that would occur if components were treated as independent when they are not. Outliers and non-Gaussian tails appear naturally. A few epochs may have poor seeing or guiding and yield centroids that sit far from the trend. Robust fitting downweights such points rather than forcing them to dominate the slope. A few spectral orders may contain unmodelled blends that bias velocities in that window. The velocity is then formed from clean regions with explicit rejection of contaminated orders. The remaining distributions in proper motion and radial velocity can have slight wings that extend beyond a simple bell shape. Sampling methods accommodate such wings without compressing them into an unrealistically narrow core. Internal consistency supplies cross-checks that can reveal hidden problems. A distance combined with effective temperature and gravity implies a radius and mass that should sit within the range expected for compact helium subdwarfs. If the implied mass lies far above or below that range, either the distance or the gravity is suspect. A three-dimensional speed combined with present position should land within the broad kinematic families expected for a halo crossing. If a single component appears implausibly large given the others, a transformation step may be at fault. Independent teams analyzing the same data with different pipelines serve as an external test. Convergence supports the robustness of the outcome. Time variability tests guard against unseen companions that would modulate radial velocity. For a single compact star, velocities measured across many nights should scatter within the quoted errors without showing a sinusoidal pattern. If a small trend appears, its amplitude and period must be compared with the measurement cadence to determine whether it is physical or an alias of the schedule. Photometric steadiness over relevant timescales supports the single-star view. If an orbiting companion were present and bright enough to affect light curves, small periodic signals might appear. Their absence tightens the case that radial velocity changes, if any, are instrumental. The propagation from observables to a galactic rest frame speed is repeated many times to form a cloud of outcomes. Each point in that cloud is a full kinematic solution, a distance, a velocity vector in galactocentric components, a total speed and a comparison with the local escape speed in a sampled potential. The cloud can be sliced to report medians and credible intervals for each quantity. It can also be projected onto planes that show how uncertainties couple, such as distance versus transverse speed, or radial speed versus total speed. Such projections make transparent in plain words which piece of the measurement budget dominates the final error. For a distant halo star, distance often dominates the transverse part, while radial velocity errors are smaller because spectra carry high-precision line centers. For a nearby fast star, proper motion errors may be tiny and distance errors small, making solar motion parameters the limiting factor in the final frame. Systematic flaws are reported alongside random errors. An instrument may not measure velocities better than a few hundred meters per second in words, no matter how long the exposure. This sets a lower bound on radial velocity error. An astrometric catalogue may have a global parallax 0-point offset at the level of a few tens of microarc seconds. This sets a floor on distance. Analyses include these flaws explicitly so that formal errors do not shrink below realistic bounds, when photon statistics alone would allow smaller numbers. Finally, classification language reflects these uncertainties honestly. Rather than a sharp pronouncement, the report states that within widely used galactic potentials, and given present measurements and their errors, the object's speed exceeds the local escape speed with a confidence that can be named. The backtraced path avoids the central parsecs within its ensemble of trajectories by a margin that can be named. The identity as a hot helium-rich subdwarf is supported by spectral features that match models within their fitting residuals to a degree that can be named. Each statement is tied to an uncertainty that comes from the propagation described above, and each can be updated directly when new measurements arrive that narrow errors in proper motion, parallax or radial velocity. Close binary evolution provides a plain physical route to the speeds and surface traits recorded for a compact helium-rich star, and the pieces can be laid out without presuming details beyond what generic models require. The starting state is a pair composed of a carbon-oxygen white dwarf and a stripped helium star on an orbit, with a period measured in minutes to hours in words. Gravitational radiation slowly removes orbital energy, shrinking the separation until mass transfer begins from the helium star to the white dwarf. In this regime, the helium star is already compact and hot with a helium-dominated surface set by earlier envelope loss. Tidal forces synchronize the donor's spin with the short orbital period, imprinting rapid rotation at the surface. The stream of helium forms an accretion layer on the white dwarf, or enters more directly if the orbit is very tight, when the conditions for a thermonuclear runaway are met in the accreted helium layer, or in the core, a supernova follows that unbinds the binary. The donor loses its orbital partner in a moment, and the gravitational force that had curved its path vanishes. The donor then continues at roughly its former orbital speed along a near straight line modified by the small impulse that the expanding ejector deliver. The first observable imprint of this sequence in the survivor is its rotation. Synchronization in a minute-to-hour orbit implies a surface spin well above 100 kilometers per second, in words for a star with a small radius. Once the orbit disappears, the survivor carries this spin forward. Without a companion, strong tidal braking ceases, and only weak wind torques and internal angular momentum redistribution remain to slow the surface. The measured projected rotational speed above 100 kilometers per second fits this picture in a broad sense. The second imprint is thermal. The shell of ejector sweeps across the donor's facing hemisphere, injecting heat into shallow layers and stripping a small amount of material from the outer atmosphere. Hydrodynamic models express this as a shock that deposits energy on a dynamical timescale and inflates the outer layers slightly. After the passage, the heated skin cools on a radiative timescale that can be short compared with the travel time through the halo. The observable consequence at later times is not a persistent hotspot but a memory encoded in the overall heat content and structure, which settles to the compact high-gravity state described by spectra. The third imprint is chemical at the surface. If the donor began helium-rich, the visible atmosphere remains helium-dominated after the event. Impact stripping can further reduce any residual hydrogen that survives prior evolution, and trace elements from processed layers may be revealed or slightly enhanced. Over the months to years that follow diffusion and radiative levitation under high gravity, rearrange the photospheric composition toward the pattern typical of hot helium subdwarfs. This process is quick compared with the multi-million-year journey from launch to present location, so the currently observed helium dominance is consistent with both a pre-event helium surface and with post-impact settling under strong gravity. The fourth imprint is kinematic. The pre-event orbital velocity in such tight binaries is large. For donor radii that are small fractions of the Sun's radius, and for orbital separations of only a few donor radii, the donor's orbital speed can reach hundreds to around 1,000 kilometers per second in words. When the binary is unbound, this orbital motion becomes the survivor's space velocity to first order, a small kick from asymmetric ejector or from gravitational focusing adds or subtracts a modest amount, but the dominant term remains the inherited orbital speed. This kinematic inheritance explains naturally how a compact star emerges with the speed that exceeds the local galactic escape threshold outside the deepest central potential. The fifth imprint is the absence of a bound companion. The system that remains after the explosion contains the donor on a free path and the remnants of the white dwarf as unbound ejector. No stellar partner remains to produce radial velocity modulation or photometric eclipses. Observations that show stable radial velocity within measurement errors and steady light curves on orbital timescales therefore align with this picture. Rare cases could include a tertiary companion on a wide orbit that survives the event, but such arrangements are not required by the basic mechanism, and would reveal themselves through slow, small drifts across long baselines, rather than through fast modulation. The survivor's structural parameters fit the compact outcome. High gravity measured from pressure, broadened helium lines implies a small radius for a mass that is a fraction of the Sun's mass in words. Models of post-impact relaxation for helium stars predict that, after brief inflation, the star returns toward a compact configuration with high surface gravity and high effective temperature. The observed blue colors and strong helium features sit in this parameter space. The luminosity remains far below that of normal O-type stars because the radius is small despite the hot surface. Wind properties follow from the compactness and the high gravity. Line-driven winds scale with luminosity, and with the presence of metal lines that provide opacity. In a helium-dominated high-gravity atmosphere with modest luminosity, mass loss rates are low. The weak wind explains the slow, rotational braking and the absence of large emission features that would betray a strong outflow. It also explains why interaction with the halo medium remains negligible. The star does not build a large wind bubble and does not carry an extended fragile outer envelope that could be stripped. Spin evolution can be described in simple steps. Immediately after the event, the surface rotates rapidly. Internal coupling between the thin envelope and the compact interior can transport angular momentum inward or outward over thermal timescales. If the coupling is strong, the surface spin may drop somewhat as angular momentum spreads. If the coupling is weak, the surface retains most of its synchronized rotation. In either case, the absence of strong external torques preserves a large projected rotational speed for many millions of years, in words which matches the measured value at present. The geometry of the explosion introduces smaller symmetries, but their imprint is modest on the survivor's long-term appearance. Ejector impact excavates a shallow indentation on the facing side and strips a thin layer. The star's own gravity smooths the surface quickly and radiation spreads heat around. Any residual shape distortion dampens on a dynamical timescale that is brief compared with a year. No persistent photometric modulation from a fixed hotspot is expected at late times, which agrees with steady light curves within measurement noise. The space motion and the internal evolution proceed independently once the event ends. Gravity from the Milky Way shapes the path. The star's stored heat and nuclear fuel shape the temperature and luminosity changes. Crossing the halo does not feed back strongly on structure because the environment is thin. The survivor cools slowly and may continue helium burning for tens of millions of years depending on its mass. When that phase ends, the star contracts toward a white dwarf state with a helium-rich outer layer. At no point does the surrounding medium exert a torque or a drag large enough to alter the rotation or the speed by measurable amounts over the current timescales. Signatures in the spectrum align with this evolutionary sketch. The lack of deep hydrogen lines, the strength of helium features in multiple ionization stages, and the large projected rotational broadening form a coherent set that points to a compact helium-dominated atmosphere in rapid spin. Subtle line profile asymmetries that would indicate strong pulsations are absent at the precision reached, and the core positions of lines are stable across repeated epochs to within the radial velocity error budget already described. Photometric colors across ultraviolet and optical bands match a hot continuum with minor reddening at high latitude. Together, these traits are the expected light of a post-transfer helium star that has survived a thermonuclear disruption of its companion and now moves freely. The ensemble of imprints described above does not require detailed fine-tuning. Tight orbits produce large orbital speeds and strong tidal locking. Thermonuclear disruption in such orbits unbinds the system and releases the donor at its orbital speed with rapid spin. Impact heating and stripping modify the outer layers in ways that relax quickly toward the generic helium subdwarf pattern under high gravity. Weak winds preserve rotation over multi-million-year spans. Each step follows from basic gravitational dynamics and radiative processes and is expressed here in plain words tied to observables that spectra and time series support. Reproducible measurement chains allow independent teams to rebuild the motion identity and environment of a fast helium subdwarf from first principles. The chain begins with astrometric time series. Each epoch stores pixel coordinates, fluxes point spread function parameters, background levels, and the transformation to a sky grid defined by distant galaxies. The reduction records the distortion map of the focal plane, the color terms applied to positions, and the covariance matrix that couples right ascension, declination, parallax, and proper motion. Timestamps tie to an atomic clock standard and include exposure midpoints corrected to the solar system barycenter in words. With these elements present, the fit for linear drift and annual wobble can be reconstructed and stress-tested under alternative weighting schemes. The spectroscopic branch mirrors this structure. Raw frames include bias, dark flat, and calibration exposures, with lamp or comb identifiers and temperatures logged. Each extracted order carries a wavelength solution, with residuals, blaze correction vectors, signal per pixel masks for telluric regions, and flags for blends. The pipeline notes the instrumental profile used in line fitting and the stability metrics for each night. Co-added spectra are stored alongside per-exposure products, so that velocity scatter can be checked rather than assumed. Templates used for cross-correlation or forward modeling are versioned with line lists, broadening kernels, and atmosphere grid identifiers so that template mismatch can be quantified rather than guessed. Photometric inputs assemble into a third branch. Calibrated magnitudes in multiple bands include 0 points extinction, coefficients for the night aperture corrections, and reference catalogues for color terms. For time series, cadence, exposure time, and image quality indicators are logged so that subtle variability tests can distinguish instrumental systematics from real changes. The maps used for dust corrections are cited with versions, and neighbouring sight lines are retrieved to bracket reddening in a small angular patch, appropriate for a high-latitude field. The parallax proper motion solution and the spectroscopic velocity then meet in a kinematic merge. At this step, the adopted solar peculiar motion and the local circular speed are included explicitly as sampled parameters with stated priors in words. The transformation to a non-rotating galactocentric frame is coded as a sequence of rotations and vector additions that cite the coordinate system definition used for galactic longitude 0 and pole. Position and velocity components are then expressed in a common Cartesian frame centered on the Milky Way's center. The code stores not only the final velocity vector but also the random seed and sampling draws, so that the cloud of outcomes can be regenerated byte for byte. Distance enters through a dual channel. The parallax distribution is sampled in native units, with its reported covariance against proper motion. Photometric distance uses a grid of helium-dominated high-gravity atmospheres with specified microturbulence and metallicity assumptions. The grid returns absolute brightness in standard bands for each pair of temperature and gravity that fits the spectrum within line profile residuals. The two distance channels combine as a product of likelihoods rather than as a single substituted number, leaving the natural asymmetry of parallax inversion intact. From the merged distance distribution, the transverse kilometers per second follow in a linear step. The total space speed comes from adding transverse and radial components in quadrature in words. Each trial reports the speed and its split into outward rotational and vertical components with respect to the galactic center. The galactic potential used for escape speed and backward integration is versioned with its bulge disk and halo parameters and with citations to the traces that constrained it. The local escape speed is computed from that potential at the star's present galactocentric radius and height. The comparison reports the fraction of trials above threshold for each member of a family of acceptable potentials. Orbit integrations for the backward path adopt a fixed time step that is short compared with the local dynamical time and store energy and angular momentum drift per step, so that numerical accuracy can be audited. The ensemble of past trajectories records plane-crossing locations and times with uncertainties derived from the input spread. Spectral classification proceeds on a parallel documented path. Helium line ratios and the absence or weakness of hydrogen series features are measured with fits that separate rotational thermal pressure and instrumental broadening. The projected rotational speed arises from a joint fit to several unblended helium lines using the same rotational kernel across lines. The spread in best fits across lines becomes part of the uncertainty. Surface gravity follows from pressure-sensitive wings. Effective temperature follows from ionization balance among helium lines and from the continuum shape when flux calibration supports it. Abundance estimates for light metals come from weak features measured in high resolution. Each parameter carries its own posterior distribution rather than a single value. Downstream steps sample from these distributions so that composition and atmosphere choices propagate into absolute brightness and thus into distance. Photometric steadiness and radial velocity stability tests follow a uniform protocol. Periodograms search for coherent signals in the light curve over the sampled cadence. None yield significant peaks above a false alarm threshold, tuned to the noise properties of the dataset. Radial velocities across epochs are fitted with a constant plus white noise model and compared with circular orbit models over periods from hours to years expressed in words. the constant model remains favored within quoted precision. These tests set upper limits on companions that would disturb the kinematics relevant to the hypervelocity label. Error accounting remains explicit. Random components from photon statistics, centroiding noise, and wavelength fit residuals appear as diagonal terms. Shared systematics such as a parallax 0 point offset a spectrograph drift flaw, or a global shift in the adopted circular speed appear as common draws applied to all trials in a run, so that their effect on the final speed distribution is not diluted. Covariances from the astrometric catalogue are honoured by drawing samples from the full covariance matrix, preserving correlations between parallax and proper motion components that would otherwise compress uncertainties. Model dependence is isolated and reported. Alternative atmosphere grids for helium-dominated high-gravity stars are swapped into the photometric distance branch to test sensitivity to line lists and microphysics. Alternative galactic potentials within a constrained family are swapped into the escape speed and integration branch. Alternative solar motion values within accepted bounds are sampled. The resulting spread in total speeds escape comparisons and back-traced plane crossings is then quoted as model variance separate from observational variance so that each source of uncertainty is visible. Data provenance ties the branches together. Each number plotted or quoted points back to raw frames, calibration files, pipeline version hashes and configuration settings. The full chain sits in a workflow that can be rerun end-to-end, producing identical results when inputs and settings are unchanged. If a new parallax release appears, the astrometric branch alone can be updated, while the spectroscopic and photometric branches remain fixed, and the merge step reruns to yield revised speeds with a changelog that lists only the altered inputs. If a new spectrum with higher resolution arrives, the spectroscopic branch refreshes line profiles, projected rotational speed and radial velocity, and the downstream photometric and kinematic parts update accordingly. Presentation avoids compression into single headline numbers when distributions carry structure. Speeds appear with central values and credible intervals that reflect a symmetry inherited from distance. Plane crossing maps display density of trajectories rather than a single crossing point. Identity parameters for temperature, gravity, and projected rotation appear with their posterior spreads. The halo environment description relies on public large-scale maps of gas dust and magnetic proxies that are cited with versions and sky coverage. The line of sight used for color corrections and for environmental context is recorded in galactic longitude and latitude so that the same path can be retrieved. With these practices in place, independent groups can rebuild the astrometry spectroscopy, photometry frame, transformations, distance, inference speed, comparison with escape thresholds, trajectory integration, and spectral identity without appeal to undocumented steps. The outcome is a set of reproducible version products that describe a hot helium-rich compact star moving in the galactic halo with a speed expressed in the non-rotating galactocentric frame, and with uncertainties that arise from transparent sources in the measurement and model chain.